In this lesson, we present three famous theorems in number theory called Wilson's theorem, Euler's theorem, and Fermat's little theorem. Well, as a homework exercise, we showed that if you have a congruence, x squared congruent to 1 mod p, where p is prime, we showed that the only solutions are x congruent to plus or minus 1 mod p. So if we look at this expression, x squared is congruent to 1 mod p, we see that x times x is congruent to 1. So in other words, x is its own inverse, and so therefore the only numbers that are their own inverse mod p are 1 and negative 1. So x is its own inverse mod p, because x times x is congruent to 1 mod p. We see that so x is its own inverse if and only if x is congruent to 1 or minus 1 mod p. So x is its own inverse if and only if x is congruent to 1 mod p or x is congruent to negative 1 mod p. So we will need this fact when we prove Wilson's theorem. So let's see Wilson's theorem. If p is prime, then p minus 1 factorial, so which would be p minus 1 times p minus 2 times p minus 3 all the way down to 3 times 2 times 1. So p minus 1 factorial will be congruent to negative 1 mod p. And if you think of it as a statement about divisibility, we see that p divides p minus 1 factorial plus 1. It's another way of stating Wilson's theorem. So let's begin the proof. So we need a prime number, so suppose p is prime. Then look at the numbers 1 through p minus 1, the positive integers 1 through p minus 1. So there's p minus 1 of those numbers. So look at the p minus 1 positive integers one, 2, 3, all the way up to p minus 1. Now each of these numbers is relatively prime to p. So we've proven that each one would therefore have a unique inverse mod p. Okay, so since each of these integers is relatively prime to p, each one has a unique inverse mod p. Now we've already shown that the only two numbers that are their own inverses would be 1 and -1 mod p. So in this list, the numbers 1 and the numbers p minus 1 would be their own inverse. So we have shown that the only two integers that are their own inverses are 1 and p minus 1. Because p minus 1 is -1 mod p. So the other numbers in this list, 2 through p minus 2, we can match each one of those numbers up with its unique inverse. So we can pair up the integers 2 through p minus 2 we'll match them up, and we're going to multiply them together with its inverse. So each with its inverse. And when we multiply them together, we get that 2 times 3 times 4 all the way up to p minus 2. We multiply all these integers up together, that should be congruent to 1 mod p. Because when I pair them up, each number with its inverse, we'll just get a product of 1 a bunch of times. So we're pretty close to the statement. We just need to add the factors 1 and p minus 1. If I multiply both sides of this congruence by 1, that won't affect anything. When I multiply both sides of the congruence by p minus 1, we get when we multiply this expression by 1 and p minus 1, this gives 1 times 2 times 3 all the way up to p minus 2 times p minus 1. And that will be congruent to p minus 1 mod p. But this is congruent to -1 mod p. So when we look at this, we see that p minus 1 factorial is congruent to -1 mod p. And that finishes the proof of Wilson's theorem. So let's look at an example of Wilson's theorem. Well, we know that since 13 is prime, that 12 factorial must be congruent to -1 mod 13. I'm going to play around with this left-hand side of this congruence. So the factors 1 through 12 multiplied together are congruent to -1 mod 13. I'm going to replace the factors 7 through 12 with a negative residue. So I'm going to rewrite this as 1 times 2 times 3 times 4 times 5 times 6. And then 7, I'm going to think of that as negative 6 mod 13. 8 would be negative 5. 9, negative 4 mod 13. 10 would be negative 3. 11 is negative 2. And 12 would be negative 1 mod 13. The reason I'm doing this is because I can combine these two expressions. You see I have the factors 1, 2, 3, 4, 5, 6, which is 6 factorial. Then I also have another factor of 6, 5, 4, 3, 2, and 1. So it's another 6 factorial. And I can factor out all the minus signs. So we see this equals 1 times 2 times 3 times 4 times 5 times 6. If I factor all the minus signs, this is another 6 times 5 times 4 times 3 times 2 times 1. And I have a total of 6 factors of negative 1. So it's negative 1 to the power 6. So I can rewrite this as 6 factorial. And I have 2 factors of 6 factorial. So it's 6 factorial, the quantity squared. Now the minus 1 to the 6th power is just equal to 1. So negative 1 to the 6th power is congruent to 1 mod 13. So that would just kind of cancel. And so the left-hand side simplifies to 6 factorial, the quantity squared. We see that that's congruent to negative 1 mod 13. So by doing this trick, we actually get a little theorem. Let's just call this a fact. I'm not going to prove this right now, but a fact. So if P is congruent to 1 mod 4, so for example 13 is a prime that's congruent to 1 mod 4, then by following the same procedure we just did, you can always show that if I take P minus 1 and divide it by 2, I take this number factorial, square it, then it'll always be congruent to negative 1 mod P. So now I'm going to actually prove the converse of Wilson's theorem. So Wilson's theorem says that if P is prime, then P minus 1 factorial is congruent to negative 1 mod P. But now I will show that if you have a positive integer greater than or equal to 2, and it satisfies this congruence, then the modulus must be prime. So if m is a positive integer, that's bigger than 2, or greater than or equal to 2, and further, m minus 1 factorial is congruent to negative 1 mod m, then we will show that the only way this is possible is if m is prime. So we proceed by contradiction. So for the sake of contradiction, suppose m is composite. Well, then we can write m as a product of integers. So let's say m equals a times b where a and b are proper divisors, so they're not equal to 1 or m. So m equals a times b for some integers a and b. That are between 1 and m. So let's say 1 is less than a, which might be less than or equal to b, and they're strictly less than m. So in other words, m has some proper divisors. Now we have a is a divisor of m. So since a divides m, and we're assuming that m minus 1 factorial is congruent to negative 1 mod m, so therefore m divides m minus 1 factorial plus 1. Since a divides m and m divides this other integer, then a also divides this integer m minus 1 factorial plus 1. A also divides m minus 1 factorial plus 1. But a is an integer between 1 and m, so therefore a will divide m minus 1 factorial. Okay, so since a is between 1 and m, and a is an integer, a also divides m minus 1 factorial. So the last two statements, if a divides m minus 1 factorial plus 1 and a divides m minus 1 factorial, then it will divide any linear combination of these two. Therefore, we can say that a divides m minus 1 factorial plus 1 minus m minus 1 factorial, which is a linear combination of these two expressions. But this just equals 1. Therefore, a divides 1. But this contradicts the fact that a is greater than 1. Therefore, our original assumption must have been false, and m must be prime. So now we have an even stronger statement, not just the forward statement of Wilson's theorem, but we've proven the converse is true as well. Next, we will prove Euler's theorem, which would be very useful when solving congruences involving large exponents. So Euler's theorem states that if you have two relatively prime numbers, a and m, so if the greatest common divisor of a and m is 1, when I raise a to the power phi of m, so recall phi of m, the Euler phi function, counts the number of integers between 1 and m that are relatively prime to m. So if I take a and I raise it to that number, phi of m, this will be congruent to 1 mod m. So you can see this is a very useful formula because you have an expression with a number to a power, and I can simplify it by replacing it with 1 mod m, and that will greatly simplify calculations involving these types of congruences. So let's give the proof of Euler's theorem, and then we'll actually show that Fermat's little theorem is a corollary of this theorem. We'll prove that next. Okay, so let's start off with a reduced residue system mod m, we've shown that there's phi of m integers in a reduced residue system mod M. So let's let R1, R2, up to R sub phi of M be a reduced residue system mod M. So recall, this means that each of the R's are mutually incongruent mod M, and each R is relatively prime to M. So you can think of this as a set containing all the possible residues that are relatively prime to M. So from this reduced residue system, we're going to build another reduced residue system. So I claim that since A is relatively prime to M, if I multiply each of these R's by A, then I still have a reduced residue system. So claim the set A times R1, A times R2, all the way to A times R sub phi of M. This is another reduced residue system. So this is a reduced residue system. Mod M. So let's prove this claim. So we need to show that each of these ARs are relatively prime to M and they're mutually incongruent. So let's look at the proof of the claim. Since A and M are relatively prime, then A times Ri must be relatively prime to M. For each I. Okay. So because all the R's are relatively prime to M, if I multiply by another factor, which is relatively prime to M, then the product ARI is still relatively prime to M. So we need to show that the ARs are mutually incongruent. Further, the ARIs are mutually incongruent since if ARI is congruent to ARJ, mod M, then I can cancel the common factor of A by the cancellation rule because A is relatively prime to M. So if ARI is congruent to ARJ, this implies that RI is congruent to RJ mod M. And we know that the R's are mutually incongruent. This is true by the cancellation rule. So we see that the ARIs are relatively prime to M, and they are mutually incongruent. Therefore, they form a reduced residue system mod M. So that finished the proof of the claim. So we have the R's and the AR's as two reduced residue systems mod M. Then these numbers can be paired up. Each ARI must be congruent to some RJ mod M. Okay, so back to the proof of Euler's theorem. Then we can pair up each ARI with some RJ such that ARI is congruent to RJ mod M. So this is true because if you have two reduced residue systems mod M, then each set contains the same residues mod M. So let's multiply all the R's together and all the AR's together. If I multiply R1 times R2 all the way out to R sub phi of M, well, each one of these R's is congruent to one of the ARI's, so this product will be congruent to the product AR1 times AR2 all the way up to AR sub phi of M. But this expression, if I can pull all the A's to the front, we'll see this is congruent to A, and I have a total of phi of M factors of A. So we get A to the power phi of M times the product of the R's, R1, R2, all the way to R sub phi of M mod M. But each one of the R's are relatively prime to M, so we can cancel all the R's. So we can cancel all the RI's. Because they're relatively prime to M. And when we cancel all the R's, we just get A to the phi of M on one side, and that must be congruent to 1 mod M. So this finishes the proof of Euler's theorem. So let's look at some examples of Euler's theorem. So phi of 10. We know that 10 is 2 times 5, and so we can quickly evaluate phi of 10 to be equal to 4. It'll be 1 times 4, which is 4. So if you take any number relatively prime to 10, for example 3, 3 to the power 4 would therefore be congruent to 1 mod 10. So we know this is true by Euler's theorem, but let's look at 3 to the power 4. What is 3 to the power 4? 3 to the power 4 is 81, and that is definitely congruent to 1 mod 10. 81 is 1 more than a multiple of 10. What about phi of 9? Phi of 9 is 6. There's 6 numbers between 1 and 9 that are relatively prime to 9. So if I take a number that's relatively prime to 9, for example 2, 2 to the power 6 must be congruent to 1 mod 9. Let's verify. 2 to the power 6 is 64. And since 63 is a multiple of 9, we see that 2 to the 6 is indeed congruent to 1 mod 9. Let's do something a little bit less trivial. Phi of 11, 11 being prime, phi of 11 would be 10. So let's take a number that's relatively prime to 11, like 8. What if I wanted to simplify 8 to the power 10 mod 11? Well, we know that 8 to the power 10 must be congruent to 1 mod 11. But what is 8 to the power 10? 8 to the power 10 is 1,073,741,824. So even with relatively small numbers, these powers can get quite large. 8 to the power 10 is already over 1 billion. So if we're going to work mod 11, this is a great simplification. That you can just simplify 8 to the power 10 with 1 mod 11. Now we'll prove Fermat's little theorem, which is named Fermat's little theorem to distinguish it from the famous Fermat's last theorem. So Fermat's little theorem is now actually just a corollary of Euler's theorem. And it was actually Euler who gave the first proof of Fermat's theorem. Fermat conjectured this theorem. Euler gave the first proof, and he extended it with his theorem. So let's look at Fermat's little theorem. So Fermat's theorem says if P is prime, then A to the power P is congruent to A mod P. If P does not divide A, then I can actually divide both sides. This is congruence by A to obtain an alternate form of Fermat's little theorem. So if P does not divide A, then we see that A to the power P minus 1 is congruent to 1 mod P. So there are two forms of Fermat's little theorem. Let's give the proof. It'll be very short because we've already got Euler's theorem. So if P does divide A, then A to a power P is still a multiple of P, so therefore that would be congruent to 0 mod P, and that would be congruent to A mod P, which is also a multiple of P. So the theorem holds trivially if P divides A. So let's assume that P does not divide A. If P does not divide A, then P and A must be relatively prime. And by Euler's theorem, it tells us so A to the P minus 1 power, which is A to the phi of P. Remember, if P is prime, then phi of P is P minus 1. So that would be congruent to 1 mod P. So we've established that A to the P minus 1 is congruent to 1 mod P, and then by multiplying both sides of this congruence by A, we get that a to the p must be congruent to a mod p. So this was Fermat's little theorem, which he actually conjectured before Euler proved his theorem. So next I'll give a corollary of Fermat's theorem. If p is prime, and p does not divide a, then a to the power p minus 2 must be the inverse of a mod p. This corollary has a quick proof using Fermat's theorem. So if p does not divide a, then a to the power p minus 2 times a would equal a to the p minus 1, which Fermat's theorem tells us is congruent to 1 mod p. Therefore, a inverse is a to the p minus 2. To finish up this lesson, I'd like to give some examples of how to use Euler's theorem and Fermat's theorem. So for example, let's find 2 to the power 123 mod 11. Well, 11 is prime, and by Fermat's little theorem, we know that 2 to the power 10 must be congruent to 1 mod 11. So, by Fermat's little theorem, two to the power 10 is congruent to 1 mod 11. So I'm going to break up 2 to the power 123 in a way that I can take advantage of this fact. Then 2 to the power 123, well, if I look at 120 is a multiple of 10, so I can write this as 2 to the power 120 times 2 cubed, and 2 to the power 120 is 2 to the power 10 raised to the 12th power. So I multiply exponents, 10 times 12, I get 120, so times 2 to the 3rd power. Well, 2 to the 10th is congruent to 1, so this is just 1 to the power 12 times 2 to the power 3. 1 to the 12th is 1, 2 cubed is 8, so therefore 2 to the power 123 is congruent to 8 mod 11. So we don't need to multiply 2 to the power 123 and then divide by 11 to figure out the remainder. We can simplify greatly using Fermat's theorem. Let's look at another example of Euler's theorem. What I want to know is, what are the last 3 digits of 7 to the power 803? Okay. So if you try to multiply 7 to the power 803 on a calculator, you would definitely not be able to look at the last 3 digits. It would give you some kind of decimal approximation in scientific notation. Well, using number theory, we can answer this question by looking at 7 to the power 803 mod 1000. So the last 3 digits would be the remainder when this number is divided by 1,000. So we can answer this question by computing 7 to the power 803 mod 1000 and using Euler's theorem. Well, the only primes that divide 1,000 are 2 and 5. So phi of 1,000 would be 1,000 times 1 minus 1/2 times 1 minus 1/5. And when you simplify this, this equals 400. So phi of 1,000 is 400. So we know by Euler's theorem that 7 to the power 400 will be congruent to 1 mod 1,000. So this will help us greatly simplify this problem. Then 7 to the power 803, which equals 7 to the power 400 squared times 7 cubed. So 7 to the power 400 squared would be 7 to the power 800 times 7 cubed would give me 803 factors of 7. But 7 to the power 400 is just 1 mod 1,000, so this is just congruent to 7 cubed, or 343 mod 1,000. Therefore, we can conclude that the last 3 digits are 3, 4, and 3. So we see that Euler's theorem and Fermat's little theorem will greatly simplify our expressions with large exponents. So I really want to emphasize this, so I'm going to call this a real big idea from this lesson. To solve a congruence where you have a large exponent, so to solve a congruence like a to the power k mod m, where a and m are relatively prime, you should really reduce the exponent using phi of m. So you should work mod phi of m in the exponent. So the idea is, if you can write k as some quotient times phi of m plus r, some remainder r, then a to the power k will be congruent to a to the power r mod m. So I'm really working mod phi of m in the exponent. So if a is q times phi of m plus r, then a to the k will be equal to a to the q times phi of m plus r. But I can rewrite this as a to the phi of m raised to the power q times a to the power r. And the expression a to the phi of m will just simplify to 1 mod m. So therefore, this is congruent to a to the r mod m. So this is the big idea. To solve these congruences, we will reduce the exponent mod phi of m, as long as a and m are relatively prime.